In this Excel example, testing for two population means mu sub 1 and mu sub 2, they are equal or not, and assuming that the two samples are independent random samples and the population standard deviations are unknown but equal. So that's the condition, and we're going to revisit one of the examples that we've seen in the past. This is weekly sales of a new cola that a company is introducing, and we want to test whether the weekly sales is different depending upon the placement of this new product. So we are looking at two possible locations. In the first population is where we're going to place the new product using what is called the beverage end cap location. And the second population is the produce end cap location. So there are two possible locations. So we're going to randomly select grocery stores and assign one group to the beverage end cap location, and then the remaining randomly select the remaining stores and assign them for produce end. And then we are collecting data from these stores, and the data is weekly sales. So this is the two independent random samples because they are not related in any way. So here is the data given. Okay, so let's go to Excel now and complete the test. So here we have the general notations that we're going to be following. X sub 1 is the observations from population 1, X sub 2 from population 2. Mu sub 1 and mu sub 2 are the two population means. Sigma squared sub 1, sigma squared sub 2, the two population variances, and these are the three possible ways in which we can set up the hypothesis. And then we're going to have independent random samples. N sub 1, N sub 2 are the sample sizes. X bar sub 1 and X bar sub 2 are the sample means. And S squared sub 1, S squared sub 2 are the two sample variances. Okay. So let's look at the problem that we just looked at from the textbook. So here X sub 1 can be defined as the weekly sales of the new cola for the beverage end cap location. So that's X sub 1, and therefore mu sub 1 is the population mean weekly sales for that location. Now X sub 2 is the weekly sales of the new cola when we use the produce end as the location. And mu sub 2 is the population mean weekly sales. Now we want to test whether there is any difference between these two possible locations for display. So our null hypothesis is that the two population means are equal. The alternative is they are not equal. And let's assume alpha of 5%. Now the data is given. So let's find the sample statistics count of that would be the sample size for sample 1, and then average will be the sample mean, and then we do stdev.s, so that will be the standard deviation for sample. Okay, so now we copy that over. That's for sample 2. So now we have all the sample statistics that we need, and let's state the assumptions required. We've already gone over the assumptions several times, so let's state them explicitly here. So samples are small, well here the samples are small, and therefore we have to assume that the population is normally distributed. So we cannot avoid this, because if the samples are 30 or more, then we don't have to make this assumption. Now assume that the two populations have the same standard deviation, and of course the samples are independent. So now we're going to compute the pooled variance estimate, and the formula for pooled variance estimate is right here. So we're going to use that formula. Let's move this formula closer so we can follow the formula along. Okay. So we need to start with two parentheses, n sub 1 minus 1 times s sub 1 squared, okay, plus n sub 2 minus 1 times s sub 2 squared. Okay, so that's the numerator, and then the denominator is n sub 1 plus n sub 2 minus 2. Okay, and that's our pooled variance estimate. So this is the variance. So when we have long formulas like this, it is probably a good idea to split it up into smaller segments, so the chances of error is minimized. So what I would do is, okay, let's separate this. So we'll compute that part like n sub 1 minus 1 times that square. So that's that part for sample 1. So now we can copy this over. Now when you add those two, then we get the numerator. So add the two. Okay, and then we can add n sub 1 plus n sub 2 minus 2. Okay. And now you say the pooled variance estimate is simply, that's the numerator divided by the denominator. So we'll give you, of course, the same answer, but you're breaking it down into smaller pieces, thus minimizing chances of error. Now standard error of estimate, okay, so that's the denominator part here. Okay, so let's move this formula closer. Okay, so the denominator part, so that will be square root of, okay, that pooled variance times 1 over n sub 1 plus 1 over n sub 2. So that will give us the standard error of estimate. So then T stat is x bar sub 1 minus x bar sub 2. Okay. Now we need to subtract the hypothesized value for that difference, which is what is the value of the difference in the hypothesis. So the value of the difference in the hypothesis is 0. So we have minus 0. We can skip that. Then divided by the standard error of estimate. That will give us the value for the T statistic. The degrees of freedom, remember, is n sub 1 plus n sub 2 minus 2, which we have here. Okay. So now to arrive at the conclusion, we can do a t-table approach or a p-value. We will do both table and the p-value. So t-table here is a two-tailed test. So we have t dot inv dot 2t. The probability is 5%. Degrees of freedom is 18. So like that. So that gives us the t-table value. And now we can say that since the absolute value, so in a two-tailed test, you take the absolute value of the t statistic, and if that is greater than the t-table value, we'll reject, otherwise we will not reject. So in this case, it is, the absolute value is greater than 2.1, so we will reject. The p-value is t dot dist dot 2t. Okay, so two tails. So here we have to provide a positive value for x. So which means we have to always do for a two-tailed test absolute value of the t statistic and then the degrees of freedom. So that gives us 0.7%, which is less than 5%, so we will reject. Okay, so our conclusion is, so we have sufficient sample evidence to conclude that the average weekly sales for the new cola for the two different locations are not the same. The probability that this conclusion is wrong is very small, 0.7%. Now we can do one more thing when we make a conclusion like this to verify the assumptions that we made. The assumption being that the two population standard deviations are the same. So one thing you can do is you can prepare some visual charts, one chart being a box plot for the two samples. So let's do the box plots for these two samples, and we will go to StatCrunch from my StatLab website. So let's go to the website. So here's, and the data set for this is available from the textbook, so we'll click that. So chapter 10, I think it is under cola. So now we have beverage location and then produce location. Okay, so go to graph, box plot, beverage, compute. So we have that, and then produce location. Now to compare the two box plots, it's a good idea to make sure that the y-axis has the same range in both the plots. So this one goes from 20 to 80. Okay, let's make this also go from, this one goes from 0 to 90, so we'll have this go from 0 to 90 as well. Y-axis 0 to 90. Okay, and let's make sure that this is also from 0 to 90. Okay, now we can copy paste these into the Excel file, and we'll have more context as to the assumptions. So if you look at the assumption of equal standard deviation, it's kind of questionable whether the two standard deviations are equal. So there are some problems with this test that this plot reveals to us.